this is Razika and this is the 6th session of the Ray Optics and Optical Instruments chapter. Okay, so we will just revise what we have discussed in the previous classes. We had discussed few basic definitions regarding the spherical surfaces with respect to the refraction, and we had derived one formula which will be asked for 5 marks, that is refraction through a spherical surface. And that case which we have derived was when the object is placed in rarer medium and image formed is in denser medium. The next thing which we discussed was lens and its types. So there are two types of lenses, concave and convex lens. Then we had discussed about types of images and image formation in case of lenses. Fine. Now, in today's session, we will discuss a very important concept, that is the lens maker's formula. So this lens maker's formula will be asked for 5 marks.
Now, before we start discussing or deriving the lens maker's formula, we need to know few basic things related to convex lens and concave lens. Okay, as you can see, this convex lens is actually a combination of two spherical surfaces. Okay, I can consider this as one spherical surface and this as the second spherical surface. Similarly, in concave lens also there is a combination of two spherical surfaces. This is one spherical surface and this is also another spherical surface. Okay, so since these convex lens and concave lenses are combination of two spherical surfaces, each convex lens will have two radii of curvatures and two centers of curvatures. Okay, see here they have mentioned convex lens, concave lens, which means we are quoting here the biconvex lens or double convex lens. If I simply say convex lens, you need to understand I am referring the biconvex lens or double convex lens. Similarly, concave lens means a double concave lens or biconcave lens. Okay, if you look at this figure, you can see here this is the lens part. Fine, and you can see this is derived from two solid spheres. Solid spheres in the sense they are refracting spheres. So this is the first sphere and this is the second sphere, which means on the right hand side you have first sphere and on the left hand side you have the second sphere. Fine. So since the first part of the spherical surface forms the sphere on its right hand side, the center of curvature will also be located on the right hand side. Similarly, the radius of curvature will also be located on the right hand side. Now next, since the second part of the convex lens is having the sphere on its left side, its center of curvature is also on left side and the radius of curvature will also be on the left side. Okay, one thing here which you need to remember is, see, as I said, the double convex lens is a combination of two spherical surfaces. It is not always necessary that these two spheres must have same radii of curvatures. There can be different radii of curvatures also. As you can see here, Okay, this is a double convex lens. So the first part of the lens, which is on the left hand side, this one is the first part. So for this first part, the sphere forms on the right side. Fine. So this sphere is bigger compared to the sphere, which means it is not always required that R1 is equal to R2. There can be certain cases where R1 is not equal to R2. Okay. Similarly, if you can see this concave lens, same thing happens here. This concave lens, since it is a biconcave lens, it will have two centers of curvatures. Similarly, two radii of curvatures. Okay, this is the basic for the double convex lens and double concave lens. So over this we will be deriving lens maker's formula. Now let's discuss about the lens maker's formula. Okay, so this lens maker's formula derivation will be asked for 5 marks. The question can be asked like obtain lens maker's formula. Okay, now we'll see why this lens maker's formula is called by this name. This formula is used by lens makers for preparing lenses of definite focal lengths. Okay, now as you can see here, there is a convex lens, and I'll draw the principal axis for this convex lens. So this is the principal axis. Now I'm going to name the lens. This is A, B, C, and this is D. So this lens is made of material of refractive index N2, and the surrounding medium is having the refractive index N1, which means here the refractive index will be N1. Here also the refractive index will be N1. Only in the center the lens will have different refractive index, that is N2. So here this point is called as the optical center of the lens. Okay, this is not the pole, this is optical center. So this optical center means here the ray which is incident will not show any deviation. Okay, that is when it strikes or when it passes through the optical center. Fine. So what we have taken here, we have taken one convex lens of refractive index N2. The surrounding medium is having the refractive index N1. Here this N1 is the refractive index of rarer medium, and this N2 is a refractive index of denser medium. Fine. So in the rarer medium, what I am going to do, I am going to place one object O. Okay. So as you know, the convex lens, which I mean is a double convex lens, is made of two spherical surfaces. Okay. So if the two spheres are there, for this sphere the radius of curvature will be on this side, and for this sphere the radius of curvature will be on this side, which means this double convex lens will have two radii of curvature, two centers of curvature, as well as two normals. Because we know how to draw the normal, a straight line which passes through the center of curvature and point of incidence. So since there are two normals for this, you will have two images. Okay, so first image is produced by this lens, this half of the lens. Okay, first image is produced by this half of the lens, and second is produced by this half of the lens. Okay, I'll explain it in detail once again. So let me draw the incident ray. Okay, this is the incident ray. It falls at N1. So from here actually there will be two images formed. This will be the first image I1 and another image which is final image I. I'll tell you later how these images are formed exactly. Okay, so here in this derivation of lens maker's formula, you need to draw 3 ray diagrams. So this is the first ray diagram. Okay, where we have kept one object in rarer medium and the images, two images are formed, I1 and I. Okay. Now the distance from here to here, that is the distance between the object and the pole, is represented by U. The distance from I1 to the pole is represented by V1. This is the distance of first image, so I am calling it as V1. Next, the distance between I and pole is V. It says final image. Okay, so this is figure 1. Now next, what we have to do, for the derivation, we have to consider refraction through two spherical surface. So let me write, I am going to consider. Now we are going to discuss the refraction through the first spherical surface. Okay, the first spherical, as you can see in the ray diagram, is A, B, C. Here it is A, B and C. Why are we considering refraction twice here? Because as I said earlier, this convex lens is actually a biconvex lens, which means combination of two spherical surfaces. So this convex lens will have two radii of curvatures, two centers of curvatures. Since we draw the refracted ray with respect to the normal, either away from the normal or towards the normal, we need to consider refraction 2 times. Fine. Now let me consider the first spherical surface. Okay. I'll draw the principal axis for this spherical surface. Okay. I'm going to name the spherical surface. You know this is A, B and C. Fine. Like this. So this is our first spherical surface of refractive index N2. Here the refractive index is N1. As I said earlier, I am going to place one object O here. Okay, and this object O will emit ray of light which incident on the spherical surface. Okay, so this is O. A is the incident ray which strikes this spherical surface. Now since this ray of light is traveling from one medium to another medium, what should happen? Refraction has to take place. Either this ray will bend towards or away from the normal. Okay, if it is traveling from rarer to denser medium, it will bend towards the normal. If it is traveling from denser to rarer medium, it will bend away from the normal. So before we draw the refracted ray, we need to mark center of curvature. So for this spherical surface, the center of curvature is here. Since we have two centers of curvature, I am going to represent one center of curvature as C1, another as C2. How to draw the normal? Straight line passing from center of curvature to the point of incidence. So this is our normal. The red line is representing the normal. Now let's draw the refracted ray. Okay, actually the light has to pass like this, but since it is traveling from rarer to denser medium, it will bend towards the normal. Okay, mention the direction, which is very important. Fine. Now this image I'll name as I1 because this is the image produced by the first spherical surface. Now the distance from object to the pole, we know it is u. The distance from the pole to the image I1 is represented by V1. Since it is first image, I am going to represent it as V1. The distance from this pole to the center of curvature is R1. Okay. Now, in the previous session, we had discussed about refraction through a spherical surface. And that was the case when the object is in rarer medium and the image formed is in denser medium. So, where was the object? It was in rarer medium. So, for that, we already had got one equation, that is N2 by V minus N1 by U is equal to N2 minus N1 by R. So, this is the general equation for refraction through a spherical surface when object is in rarer medium and image formed is in denser medium. Now, let's apply this equation to this condition. What happens? The second medium is having the refractive index same N2 divided by, in place of V, okay, we have represented image distance as V1. So, in place of V, I will write V1 minus N1 divided by U. Here, U is represented as U itself. Object distance is represented by U here. So, write it as U is equal to N2 minus N1 divided by, here we have taken R for general derivation, but here we have R1, radius of curvature R1. Okay, call it as equation number 1. What we have done here, we have considered the equation of refraction through a spherical surface when object is in rarer medium and image formed is in denser medium. Fine. So, this is the equation and this equation should be applied to this situation. What happens? Instead of V, you have to take V1 from the figure. U, we have taken U only in the figure. Instead of R, we have taken R1. So, this is about the refraction through the first spherical surface. Now, let's discuss about the refraction through the second spherical surface. Through the second spherical surface. Spherical surface. Okay. Now, considering the figure 1, the second spherical surface is ADC. It is ADC. Okay, we are going to discuss refraction through the second spherical surface now. Now, once again, you need to draw a ray diagram. Consider the second spherical surface like this. Now, draw the principal axis. So, this is the principal axis. I will draw once again. So, this is the principal axis. This point is A, this is D and this is C. Fine. Already images formed at I1. Represent that I1 here. Now, for this spherical surface, center of curvature will be this side. Okay, the center of curvature will be on the left side, that is C2. Fine. Now, first draw where the image is formed already. The image is formed at I1. This is the first image. Now let's draw the normal. How do we draw the normal? A straight line passing from the center of curvature to the point of incidence. So this is the normal. The red line is representing the normal. Now, since the light is traveling from denser to rarer medium, this lens is a denser and the outer medium is a rarer medium. So it is traveling out of the denser medium now. So it will bend away from the normal. So the light is here. You cannot get the image here because this is the ray. It should bend away from the normal like this. Somewhere here you will get the final image, and I will call that image as I. Fine. Now let's specify what are the distances which we have taken. This is V1. From the previous case, the distance from here to here we have considered as I1. This one is V, final image distance V. Initial image distance is V1, final image distance is V. And the distance from center of curvature to the pole is R2. Okay, since this is the second spherical surface, I will represent it as R2. Fine. Here, one very important thing you need to understand and need to mention in the derivation is this I1 will be acting as virtual object. Okay, for the refraction through the second spherical surface, I1 acts as virtual object, which means this is not the real object. Actually, O is the real object which formed image I1. Now for the refraction through second spherical surface, this I1 will be considered as the object, virtual object, and because of this object the final image is formed at I. Fine. You have to mention that for the refraction through the second spherical surface, I1 acts as virtual object. So in place of U, what you have to write here? You have to write V1. Okay, because this V1 is the distance of virtual object. Now another thing here is, this is the case when the object is in rarer medium, image formed is in denser medium. But here the object is in denser medium but image formed is in rarer medium. So general equation is, see, to this equation, if you take this equation, the reverse equation gives you the reverse case, which means N2 divided by, instead of V, take U with a negative sign, and here you have negative, make it positive. It is N1 divided by, instead of U, take V, is equal to, reverse it, it is N1 minus N2 divided by R. Okay. So this is the general equation for refraction through spherical surface when object is in denser medium and image formed is, image I is formed in rarer medium, Okay. Now let's apply this equation to this condition. Minus N2 divided by, instead of U, as I said, what we have to take? V1, because V1 is the object distance here, plus N1 divided by, in place of V, final image is V itself, take it as V, is equal to N1 minus N2 divided by R2. Okay, here the radius of curvature is R2. Actually here you will just get R1. Fine. Sorry, not R1, just R, general representation R. But if you apply this condition or equation to this situation, you will get R2 here. Fine. Now this is equation number 2. We have got two equations because of refraction through two spherical surfaces. This is first spherical surface, this is the second spherical surface. Now let's add equations 1 and 2. If you add equations 1 and 2, what will happen? Left hand side should be added with the left hand side and right hand side must be added with the right hand side. So N2 by V1 minus N1 by U. The second equation left hand side is minus N2 by V1 plus N1 by V is equal to, here it is N2 minus N1 by R1 plus N1 minus N2 by R2. As you can see in the left hand side, N2 by V1 will get cancelled because one is with positive, another is with negative. Write whatever is left, minus N1 by U plus N1 by V is equal to N2 minus N1 by R1. Now I will reverse it. So to reverse it, I can take negative as common. So N2 minus N1 by R2. Why am I reversing it? To take N2 minus N1 as a common factor. Fine. Now continue from here, continue solving from here. It is minus N1 by U plus N1 by V is equal to, take N2 minus N1 as common factor, remaining 1 divided by R1 minus 1 divided by R2. I will call this as equation number 3. Now in equation number 3, here on the left hand side, N1 is again common. So I will take N1 as common factor, minus 1 by U plus 1 by V is equal to N2 minus N1 into 1 by R1 minus 1 by R2. Take this N1 here. So minus 1 by U plus 1 by V is equal to N2 by N1 minus N1 by N1. I have taken this N1 here to the right hand side. So 1 by R1 minus 1 by R2. So this N1 and N1 will get cancelled here. What you will have? You will have minus 1 by U plus 1 by V is equal to, this N2 by N1 can be written as N21 minus, if N1 goes there, you will have 1 into 1 by R1 minus 1 divided by R2. Now next thing is, now let's continue solving this equation. You are left with minus 1 by U plus 1 by V equals N21 minus 1 into 1 by R1 minus 1 by R2. Now imagine this object is placed at infinity. We have discussed, if the object is placed at infinity, image will be formed at focus. So if U is equal to infinity, we know that V will be at focus. Image will be formed at focus. So substitute this here. You will have 1 by u, which is 1 by infinity plus 1 by f is equal to n2 1 minus 1 into 1 divided by r1 minus 1 divided by r2. 1 by infinity is 0 and you will have 1 by f is equal to n2 1 minus 1 into 1 divided by r1 minus 1 divided by r2. So this equation is called as the lens maker's formula. 1 by f is equal to n2 1 minus 1 into 1 by r1 minus 1 by r2 is called as lens maker's formula. Suppose if a particular focal length lens you want, by using this equation, by using the values of refractive indices, one can decide what should be the values of r1 and r2. Okay. So as I said earlier, this question will be asked for 5 marks. Obtains lens maker's formula. So this is the lens maker's formula which we have got by considering refraction through two spherical surfaces separately. Sometimes a 5 marks question will be asked, obtain a relationship between u, v and f of a lens. Again this question will also be asked for 5 marks. So we have two methods of deriving a relationship between u, v and f of a lens. One method is you can continue from here itself. The previous step of this equation is minus 1 by u plus 1 by v is equal to n2 1 minus 1 into 1 by r1 minus 1 by r2. So here in place of u we had substituted what? Infinity, and in place of v we have substituted f, because when the object is placed at infinity, image will be formed at focus. So these are the values of actually the left hand sides of this equation. As a result, what we have got? This one. Okay, if you just consider the lens maker's formula and the previous equation, what happens? The left hand sides are equal to each other. So we can write 1 by f is equal to minus 1 by u plus 1 by v, or you can also write this equation as 1 by v minus 1 by u is equal to 1 divided by f. So this is the relationship between u, v and f of a lens. You remember I hope you remember the u, v, f relationship in a mirror. There is positive here. But in case of lenses, you will have 1 by v minus 1 by u is equal to 1 by f. So if they ask you to obtain the relationship between u, v and f, you can continue the lens maker's formula and you can get this equation. Suppose if they have just asked you to derive lens maker's formula, just stop here.
Now let's quickly discuss what we have discussed in the today's session. We have discussed lens maker's formula, which will be asked for 5 marks. How to derive it? We have to take one convex lens and we have to consider refraction through two spherical surfaces. Then we get two equations and those two equations must be added and solved further. Then we had discussed about a relationship between u, v and f of a lens. That is 1 by f is equal to 1 by v minus 1 by u. So this was all for today. In the next class we will discuss about what happens when we combine the lenses, what will be the formation, how the image will be formed, or how the focal length will be when the lenses are combined together. So till then, keep studying and take care. Thank you.